Let's get started. Hello everyone, my name is Arul Selvam. I work as a technical director for Motark. So today I'm going to talk about processing telematics data using Azure EventHubs, Nodejs, and Cosmos DB. So before that, a brief intro about my company. So Motark is a connected car data and analytics software platform. So we help enterprise customers across use cases access data and actionable insights from a wide range of data sources. We work with new and emerging data sets, including the automotive OEMs directly. So this is a high-level simplified architecture diagram for one of the workflows we use. So we receive data from multiple receivers, and then we ingest the data into EventHubs. And we have multiple consumers processing the data and transform them and store them in Cosmos DB. We use App Services to expose some of the stored data via API. And we also leverage Cosmos DB Changefeed to move the data to blob storage and our data warehouses. So for those of you who are new to Azure EventHubs, it's an event streaming platform. We can potentially ingest millions of messages per second, and we can have multiple consumers concurrently processing the data at their own pace. So the reason we chose Azure EventHubs is it's fully managed service. We don't want to spend any time managing the infrastructure ourselves. So that's one of the main reasons. And then it also meets some of our enterprise customer as a compliance requirements. So it provides 99.9% SLA, and data is encrypted both transit and at rest, and it also provides geo-replication out of the box. And the total cost of ownership is very low. For ingesting 1 megabytes per second, it costs only around $20 per month. And another main reason is it provides Kafka H support. So any Kafka client can seamlessly work with Azure EventHubs. So Kafka has a rich ecosystem, so we can take advantage of that rich ecosystem. Let's discuss in detail about how we can ingest data into Azure EventHubs. So in this diagram, you can see there are multiple partitions in the EventHubs. So you need to create multiple partitions because you want to maximize the write throughput, and you also want to concurrently process the data. So I'll show you a demo. So I'll show you a demo about setting up Azure EventHubs in Azure portal. So I'm going to click create a resource. I can select EventHubs. So we need to provide a globally unique name to the EventHub. So I'm going to give build demo 2019 EH1. And for production use cases, you want to select the standard tier. And if you want Kafka support, you can enable Kafka. I'm going to skip that. And if you want geo redundancy, you can enable make this namespace zone redundant. So resource group, I'm going to select an existing resource group. And we allocate capacity to EventHubs in terms of throughput units. So one throughput unit will support 1 MB per second ingestion rate and 2 MB per second egress rate. And in case you are expecting a sudden burst of volume and you want to EventHub to automatically scale, you can enable this auto inflate. So I'm clicking create. So this will take few seconds, but when it is done, this is how it will look like. So we have created a EventHub namespace. Under this namespace, we can create multiple EventHubs. So I'm going to create one EventHub. So I'm going to call this source data 2. And we can select, I'm going to give partition count as 3. And if you want the source data to be retained for more than 1 day, you can change it. In case you want to archive the data into blob storage, you can make use of this capture. So I am going to skip that. Once creating Azure EventHubs, you can get the access keys to connect to it by clicking on the shared access policies. So I have already created a producer access key and consumer access key. The producer access key can only send data to the EventHubs, and the consumer access key can consume data from the EventHub. So I'll show you a sample code. So in this code, I have two folders, Event Processor and Event Producer. This Event Producer, I have a JSON file. It has anonymized connected car data. So let me show the packages that I'm using. So I'm using this Azure EventHubs SDK, and I'm also using this .env package. So we'll be providing the EventHub connection string and other configuration values typically as environment variables. If you use this .env package, you can keep them in this .env file. So let's look at this app.js file. So I'm importing the EventHub client module, and then in the init method, I am calling this EventHub client.create from connection string. So if you provide EventHub connection namespace endpoint and the EventHub name, it will establish a connection to the EventHub. So it will use AMQP protocol to connect to the Azure EventHubs. And I'm calling this method get hub runtime information specifically to get the partition count. So let's switch back to the slide. So at a high level, these are the steps you need to do to ingest data into EventHub. So you receive data from multiple sources, and then you can group the events by the target partition ID to which you want to ingest them data to. And in my example code, I am computing the partition ID as hash of the device serial number. Device serial number is one of the field in my events, and then I'm computing the modulo based on the EventHub partition count. So to maximize write throughput, you need to send the messages in batches. The maximum batch size is 256K. So if your message size is 1 KB, then at maximum you can send around 200 messages. Rest of the size will be used for sending some metadata. So back to the code. So I'm importing the sample data from the events.json file. And then in the main method, I am grouping the events based on the target partition ID. I am computing the target partition using this lambda expression. And then I'm iterating all the partitions. And then I'm getting the events for the target partition, and then I'm splitting them into multiple batches. And so you need to pack the messages in a field called body. And then I'm using EventHub client.sendBatch method. So this will send all the messages to the target partition. If you don't specify the partition ID, it will push the messages to all the available partitions in a round-robin fashion. So depending on your processing requirements, that may or may not be appropriate. So in my case, I want to send all messages for a given vehicle device to a same partition ID. So I'm explicitly passing the partition ID. So I'm going to run this. So it has started sending events to the different partitions. So now we can look at how we can process the data from the EventHubs. One way is you can use the Azure EventHubs library, but you will have to receive all the messages from the partitions yourselves, and then you need to keep track of managing the partitions yourselves. So you don't want multiple instances to work on the same partition. So another option is you can use the event processor host library. So there is a npm package, Azure EventHub processor host. So if you use that, it will take care of managing the partitions itself. So in this example, I'm running 2 event processor hosts. So in the EventHub, there are 4 partitions. if I run 2 instances of the event processor host, the first host will consume 2 partitions and the second host will process data from the next 2 partitions. In case if one of the instance dies, the other will take care of processing data from all the partitions. And if you think you need to add more instances to support the throughput, you can run another instance and it will automatically share the load. So at a high level, these are the steps to process the data from the EventHubs. You'll use event processor host, and then you'll run multiple instances to concurrently process data. And then in the EventHub processor host, you'll checkpoint periodically. And then if in case the process restarts after a crash, it will start processing data from the last checkpointed message. So this will result in at least once guarantee, so you need to take care of handling the duplicate events. So I'll show the code for the EventHub processor host. So I'm importing event processor host from the Azure event processor host library. So I have a thin wrapper for, so I'm going to process the data and store it in Cosmos DB. So I have written a wrapper module data store. So this is the main code. The event processor host, I am passing EventHub connection details, and I'm also passing a Azure storage connection string. So event processor host internally utilizes this Azure storage details to manage the partitions and then checkpointing the messages. So we need to call event processor host.start method. It takes 2 arguments, 2 callbacks, on message and on error. In the on message callback, you will be receiving all the messages and the partition it belongs to. So I am unpacking the data, and then I have implemented a sample transformation. If the speed exceeds greater than 80, I am going to create a speeding alert record and store it in Cosmos DB. And here I am checkpointing every 100 message. So you don't want to checkpoint for every message. It will limit the processing throughput. So now it will connect to the Azure storage, and then it will try to acquire leases for the partitions. So it will take a while. I'll also parallelly send messages. I think it's taking some time. Okay, it has processed the data and created some speeding alerts. So this is the storage account that I have configured, and I think this is not connecting. So I have created a container called EP checkpoints. So the event processor host will use this container to keep track of the leases acquired for the partitions. So for all the 3 partitions, it has created a blob file, and if you look at this blob, you will see the details of the checkpointing. So here you can see that for partition ID 0, the last checkpointed, so it hasn't processed any data from this partition. So you'll see the last checkpointed message offset here. So I'm also going to create a Cosmos DB collection to store this data. I'm going to call them sample. Okay, I'll delete this telematics collection and then recreate it. So I'm going to specify the storage capacity as unlimited, and I'm going to set serial number as the partition key for this Cosmos DB collection. Now if I run the event processor host, it should be storing data in this collection. So this is how we can process. We can run multiple instances of this, and then we can process the data concurrently. I'd like to share some of our experiences with Cosmos DB. So the reason we chose Cosmos DB is it supports elastic scalability of throughput and storage, and it also provides guaranteed low read-write latency, and this is also a fully managed service. And so in Cosmos, while creating collections in Cosmos DB, you need to create separate collections if the RU requirements and the access patterns and the TTL requirements are going to be different. So I have created a telematics collection. In case I want to store device or vehicle data, I would have created a different collection, because if you have a UI, you typically want to get all the devices and vehicles and then show it in the UI. So in the telematics collection, I have partitioned using serial number. So if I had stored the devices or vehicles in the same collection, then querying the devices and vehicles will involve cross-partition queries, and that would consume high RUs. So we have to choose the right partition key to distribute the load uniformly across the Cosmos DB partitions. And so if you want to achieve the maximum write throughput for your Cosmos DB, you have to use stored procedures. So there are some limitations with the stored procedures. Only documents with the same partition key can be stored using the single stored procedure call. So if there are multiple records with the different partition keys, then you need to make parallel stored calls to the stored procedures, passing them a different set of records. In case you want to, in case if concurrent writes are possible for the same record and you want to avoid corrupting data, you can use optimistic concurrency by leveraging the E-tags available in the Cosmos DB documents. And so we use Cosmos DB Changefeed a lot. So we use the Changefeed to move data from the Cosmos DB to our data warehouses, and also for move data to cold storage. And then we use Changefeed to update our in-memory cache of the processing node. So in the EventHub processor host, I have specified the speeding threshold as 80. In case I am storing the speeding threshold configuration in Cosmos DB, and if someone updates it using an API, I can update the in-memory cache by continuously polling the Changefeed and then updating the in-memory cache. So similar to EventHub processor host, there is a Changefeed processor library available. It works similar to the EventHub processor host. It will take care of leasing and renewing the Changefeed partitions. So you can also use Azure functions. So this is a conceptual diagram of how the Changefeed processor library works. The Cosmos DB, when you create a Cosmos DB collection, it will have multiple partitions. And the Changefeed processor library, here we are running 2 instances. And one of them is consuming data from 2 partitions, and the other one is consuming the data from the other 2 partitions. So it works exactly similar to the EventHub processor host. And these are some of the common gotchas with Cosmos DB. The default consistency level is session consistency. So if you create a record as part of a HTTP request, and if you attempt to read it as part of another request, it may not be immediately visible. And then you can update the indexing policy in your Cosmos DB. If you have a lot of data in your Cosmos DB, and then if you update the indexing policy, it will have some impact on the consistency. And there are some gotchas with the Changefeed. the deletes won't appear in your change feed, and then if there are multiple updates to your update to the same record, only the most recent update will be available in the change feed. And then there are some gotchas with the querying. If you do your order by on a field, and if some of the records don't have that field, then those records won't show up in the query result. Also, if you do a select top 100, it won't always return all the 100 records. Depending on the RU's consumption at that point of time, it might return lesser records. And if you receive a continuation token, you need to call again, passing the continuation token to get the rest of the records. And the size of the continuation token size, the size of the continuation token could be in kilobytes. So in case for implementing pagination, if you're passing the Cosmos DB token to the UI or end user, and if you're expecting them back to pass it as a query param, it may break, as it would exceed the HTTP request URL limit. So these are some of the strategies for a Cosmos DB cost reduction. You can only index the record fields. So this will reduce the write or use consumption. And then you can have a cron job to reduce the RUs allocated during the non-peak hours. And you can also parse the old data by leveraging the TTL in the collection. So if you don't need data more than data older than 3 days, you can set the TTL to 3 days. And then for some use cases, you can provision the RUs at the database level instead of at the collection level. So the minimum RUs you can allocate is 400 RUs. So if you allocate at the database level and none of your collections require high RUs, then that would reduce the cost. And in your non-production environments, you can disable geo-replication. By default, when you create a Cosmos DB account, it will have geo-replication enabled. So you will incur double the cost. We also use Azure App Services, and then we use staging slots to do zero downtime deployments. And we also use Azure DevOps to do CI/CD. So with these various Azure technologies available, we have built a really scalable platform very quickly. So these are some of the stream processing problems that we solve. We get out of order data, we get duplicate data. Some sources provide split data into multiple feeds, so we have to fetch data from multiple feeds and then join them. And some of the processing requires stateful processing. So for stateful processing, you will have to implement checkpointing the state and recovering the state in case of process restarts. So one option is you can have a background thread that checkpoints the in-memory state to your blob storage, and whenever the process restarts, you can recover the state from your blob. So that's all for the demo. So if you are interested to know more about our business, you can reach out to us. We are also hiring for these positions. Okay, thanks for joining me. I hope you found this helpful. So if you have any questions, you can ask. Yes?
A couple questions, if that's okay. For your Cosmos DB to balance out the RUs across partitions, what do you use as a partition ID?
So we use device ID. We receive data from multiple devices.
Okay.
So we use device ID.
Right. And then for the EventHub client, do you know if there's a C++ library that can be used? We're using C#, which we have. You have Node.js, but do you know if there's a C++?
I'm not sure.
Yeah, but
There is C# Java. I'm not aware of any C++. Any other questions? Yes. Sorry? Out of order data, so it depends on the requirements. So we'll use a in-memory buffer, and then we keep the data and then sort them before processing it. But it won't work for all the use cases.
I work on a product that's very similar to this. That's one of our biggest problems is handling out of order data. We have ours is stateless, so I guess it's a lot different.
Any other questions?
So when you were creating the EventHub and you had that, there was the Kafka option there.
Yes.
I don't know what that is. Can you explain?
So EventHub supports Kafka protocol. So it supports AMQP, HTTPS, and then also Kafka. If you enable Kafka, you can have all your Kafka clients to work with Azure EventHubs. So it will act as if it's Kafka.
So the default's AMQP.
Yeah.
Basically, multiple partitions, all the messages are contained. The event hubs will work as it is.
Yeah. So even EventHubs, it will maintain the order of messages that's being ingested.
Yeah, per partition.
Yeah, per partition. Okay. If no other questions, thank you. Thanks for joining me.